I hope all of you can. Okay, so as you can see the screen, so we will continue with the lesson. So first of all, actually, the thing that we have to learn about the measuring instruments is the first instrument, that is the Vernier principle and the Vernier caliper. So actually, in the last week also we touched a little bit on the Vernier principle and Vernier scale. So, but however, I will just take you again because then it will be a complete lesson on Vernier caliper, right? Okay. So, however, you have to take down the notes until we are receiving the tutorials. Please take down the notes when we are discussing the lesson, right? So, the principle of Vernier and Vernier scale, you can see here, as we discussed last week also, there are two kinds of scales that we can see. So, the problem with the normal scales or normal measuring instrument is, so if you consider a instrument with uh, what we call like let's say you are taking a measurement from a meter ruler. So the last week actually we discussed that when we are taking the measurement from a meter ruler, the least measurement that we can take is a millimeter. So when you measure smaller distances using the vernier caliper, sorry, using the meter ruler, what happens is the percentage error is much larger. So actually we need to have a lesser percentage error when we are taking a measurement. So to do that one, what we are going to do is we are actually reducing the minimum measurement or the smallest measurement. If you reduce the smallest measurement and if you increase the measurement length or the measuring quantity, then you can have a lower percentage error. So I think hope you can remember the percentage error. If you require, I can go take you there also. Here you can see here the percentage error is actually equal to the error or the minimum error or the smallest measurement, that is the least count of the instrument that we discussed, and it should be divided by the measurement and multiplied by 100. So if you have a smaller measurement and a larger least count, what will happen? You have this one is small, this one large, and you will get a larger percentage error. So this was the problem with actually the meter ruler. So if you need to take a much uh, proper in measurement or a much accurate measurement, then you have to have a lower percentage error. So the best way to have a lower percentage error is to have a least count of very small value and a measurement of larger value. So this the denominator must be larger, numerator must be smaller as much as possible. Then you can have a very low percentage error. So this is the theory. So that's why people needed new instrument to measure the lengths and everything. That's why the vernier caliper and the vernier scale came to the birth. Okay, so this is the main reason because people needed a better way of taking the measurement. Right. Now, if you take this vernier scale, you can see here, this is a simple vernier scale that you can see. So what we have done is uh, scales which are constructed by dividing range of certain number of divisions of a millimeter scale into equal parts greater than that number of divisions are called vernier scales. This may be, you may seems that it is bit confusing, but it is not that. You can take the simple idea. You don't need to remember these. These definitions you actually do not need to keep in mind. That is very clear. You don't need to keep that in mind, but you need to understand the Vernier principle. Right. If you see the diagram here, you can see there are two kinds of scales. This is the main scale. You can see here it has been divided into equal parts. That means usually the main scale is in millimeter scale. So let me put the text here, the unit here. So this is in millimeters. All the values are in millimeters, right? So now you can see bottom, there's a vernier scale And you can see here, there also we can see 10 number of divisions. 0, starting from 0, you have 10 number of divisions. But the thing is, you can see clearly here, the 10th division is actually matching with the ninth division of the main scale. That means what we have done is, we have divided 9 millimeters into 10 parts. That is what actually said here. Certain number of divisions of millimeter scale, from here it is 9, scale is divided into equal parts greater than the number of divisions. So here you can see 9 divisions. It is divided into 10 divisions in the vernier scale. So that is why actually it is called a vernier scale. Right. Hope you understand the first diagram. So basically, if you summarize it, the diagram A shows a vernier scale constructed by dividing range of 9 millimeters in a millimeter scale into 10 equal parts. Right. Now, if you go to the second figure, so if you have any questions, please raise. Okay. You can see another vernier scale here. Also, you can see in the top part is the gray color part is the millimeter scale. That is we called as the main scale. So here you can see there are 50 number of 50 and 60 number of millimeters are there. And you can see in the bottom the light color part, that is the vernier scale. So that vernier scale is bit different from this previous one. So from here you can see it. We have divided 49 number of millimeters into, if you count from here to here, there are 50 divisions, 50 equal divisions. So still this relationship is holding. The relationship that we told earlier, it still holds. And the only difference is here we have 49 divisions divided into 50 equal parts. Right. So here also we can, so let me remove this one, the previous drawing. Okay. So here in the tutorial, there's a small mistake to be corrected. So in here, it should be not 59, it should be 49 actually. 49 divisions, right. So the diagram B shows a vernier scale constructed by dividing range of 59 millimeters in a millimeter scale into 50 equal parts. So this has been done in the diagram B, right. Third one, the vernier scale can be moved along the main scale. Now I will show you a demonstration of the vernier scale a bit later. So until that, please take note of that. So the vernier scale can be moved. So this main scale is fixed actually. It is not moving to anywhere, but you can move this vernier scale over the main scale. You can slide it. So we will see a demonstration so you can clearly understand. Fourth one, if the instrument is correct, only 0 and the last mark of the vernier scale coincided with the main scale marks. So this fourth point you can clearly see here. Here you can see only the 0th mark of main scale and the 0th mark of vernier scale is coincided, and the other one is the last part of the vernier scale is coincided with the ninth division of the main scale. There are two places where vernier divisions are coinciding with the main scale. First one is the 0th one, other one is the last one, right? Okay. The distance need to move the vernier scale to coincide first mark of the main scale and first mark of vernier scale is the shortest length that can be measured. it is called the least count of the instrument, right? So it is something like that, right? So as we discussed, so what I mean by that one is, so if I enlarge this diagram, so you can see here the first part of the first division of the main scale is this one, right? So let me take the drawing, right? So now we need to focus on this part, okay? So this is the part that I'm going to focus. This first division of main scale and first division of vernier scale. This is the part that I am going to focus now. So the least count or the minimum distance between the main scale division and the vernier scale division is called the least count. So you can see here, this is the distance between zeroth mark and the first mark of the main scale. And this is the distance between zeroth mark of vernier scale and first mark of the vernier scale. And you can see here there's a small difference, length difference between these two. So this is actually what we called as the least count. This length, this small length is called as the least count, right? So all the other lengths between these main scale divisions and vernier divisions is greater than this distance. So this is called as the minimum distance. So how do you calculate the minimum distance? It is very simple. You can see here properly. So what we can do is first we can measure the length from here to here, right? So that is actually 1 millimeter. And if then you can measure the length from here to here. So if I write down the length, so here it is very clear 1 millimeter. Then what about this length? So this length is actually, you can see here, 9 number of millimeters is divided into 10 parts. Therefore, the one division of the vernier scale is actually 0.9 millimeters of length. This length is 0.9 millimeters of length. So the least count of this one will be the smaller division from here to here. That is the difference between uh, first measurement and the difference between the second measurement. So first one is 1 millimeter and this is 0.9 millimeters. Therefore, least count is 0.1 millimeter. So the least count is 0.1 millimeter here. It is 0.1 millimeters, right? I hope this is clear how to calculate the least count. So when you take an instrument with you, so you have to first calculate the least count. Without knowing the least count, we cannot actually go for the measurements, right? In the second diagram also, if I go to the second diagram also, here also, so this is the maximum magnification that I can take here. So if you take here, so the distance between 0 and the first main scale division is 1 millimeter. Then you have to find the distance between 0th division and first division of vernier scale. So you can see here 49 divisions of main scale is divided into 50 number of parts. So the you can calculate the length of a division. So that is 49 divided by 50. That is the length. So if you take the least count of that one, how do you calculate the least count? You have to you have to subtract 1 millimeter from 49 divided by 50. So this is how you calculate the least count of this vernier scale. So the distance between two vernier divisions is 49 divided by 50. Then you have to subtract that amount from the 1 millimeter. So you can take here, you take the common base, it will be 50 minus 49 divided by 50, which will finally give you 1 over 50. So that is equal to 0.02 millimeters. So it is actually given in the diagram also. So this is the least count of this vernier caliper, the vernier scale, right? So it is actually clearly mentioned in the bottom also in the tutorial. You don't need to draw the diagrams because this is bit difficult to draw and it is time wasting to draw these kinds of bigger diagrams. So just take the idea. So I have given how to calculate the uh, least count actually in a very detailed manner. So you can hear the least count is equal to length of one part of main scale minus length of one part of vernier scale. So this is how it has been calculated for the first vernier caliper. You have get 0.1 millimeter. You can see here very clearly. Here also I have taken that one similarly. So here also I have included that one very clearly so you can easily understand that one. So now if you go to calculate the percentage error, an instrument is best if the percentage error is less than 1%. Therefore, there are limitations of vernier scales. So what is here is, so for any instrument to be better for a measurement, it must have a error less than 1%. The percentage error of the instrument must be less than 1%. So now if you calculate the percentage errors of the above two vernier calipers separately, then we can find the minimum measurement that can be taken from that one. Okay, so if you calculate this one for the first vernier scale, so we know the equation, the percentage error must be less than or equal to least count divided by measurement multiplied by 100. So the percentage error is actually equal. So what we need to find is a range of measurements. That's why we are putting an inequality also. We need to find a range of measurements. Percentage error must be less, right? So the maximum permissible percentage error is 1%. So this part, the right hand side part must be less than 1%. So if you take the least count is 0.1 for this vernier caliper, and we will take x is the measurement multiplied by 100. So if you simplify this one, you can get x is greater than or equal to 10 millimeters. So what does that mean is this scale is better for measurements greater than 10 millimeter, right? If you use this vernier caliper, this first vernier caliper to take a measurement greater than 10 millimeters, then you will definitely have a percentage error less than 1%. But the problem is if you use this first vernier caliper to measure a reading or a measurement which is less than 10 millimeters. Suppose you have to measure a 5 millimeter distance. If you use this vernier caliper A, then your percentage error will be much larger. All right. So that is the thing that it is being said there. So this vernier caliper is better for measurements greater than 10 millimeters only. If you take a reading less than this, then you will have a higher percentage error. Now, if you go to the second one, here you can see that the vernier caliper B, if you do the same calculation, you can get here the x is greater than or equal to 2 millimeters. So that means this scale is better for measurements greater than 2 millimeters. So you can take any measurement greater than 2 millimeters with the percentage error less than 1%. That means you can measure 2, 3, 4, 5, any millimeters from this one. But if you are going to measure a 1.5 millimeter from this vernier caliper, then your percentage error will be more than 1%. So the best practice is not to use an instrument if that instrument is giving an error greater than 1%. That is the best practice. So that is why it is uh, said like this, right? So if not, you can use any instrument to measure anything, but the problem is your readings accuracy may be very less. So we need an accurate answer. That's why actually we are checking what are the max or what are the maximum or the minimum measurements that can be taken from each vernier calipers with maximum percentage error. So maximum percentage error is 1%. You cannot have an error more than 1%. If you are having a error more than 1%, then you should not use that instrument to take the measurements. That is actually discussed here. So now let me take you to the demonstration of the vernier caliper, right? Okay, we have a few. Okay, here. So actually, this also you can try in the internet also. I don't know whether that you have already tried this or no, not, right? So can you see the vernier scale that I am sharing? Okay, right. So you can see here, this is not a usual normal vernier caliper that you see here. This is bit different. So here, if you calculate the least count, now try to calculate the least count quickly. So here you can see there are a 39 number of divisions is divided into how many parts? 20 parts. Now you can quickly calculate, right? So you have to calculate here what will be the value, what will be the least count. Now be careful when we are reducing, okay? Here if you reduce 1 minus, if you write it like 1 minus, then the main is, so the main scale divisions is 39 divided by 20, then you are in trouble. So this is not actually correct. This is not actually correct. Because for this vernier caliper, if you look closely here, you see here the first vernier division is actually much closer to the, not to the first division, but to the second division. So when you are writing the equation, you should write not 1 minus, but you should write 2 minus, right? So it should be 2 minus, because here you can see clearly this first vernier division is very much close to the second millimeter. Let me check whether we can make it larger. So it is not getting larger properly. So, right. So now you can see actually here, you see here, the first millimeter is here, then the second millimeter is here. So the first division of vernier scale is closer to the second millimeter, not to the first millimeter. That is why actually we have to write down when we are finding the least count, it should be 2 minus 39 divided by 20. So if you cross multiply and take the common denominator, you can take as 40 minus 39 divided by 20, which will give you 1 over 20. That is equal to 0.05 millimeters. So this is the actually the least count of the shown vernier caliper, not the zero point 0.1, but 0.05 millimeters. So actually people have constructed different vernier calipers with different least counts, right? So if the in examination, if you get any kind of vernier caliper, you should be able to calculate the least count quickly. So this is how it is being done, right? So you can refer this video again if you are didn't get it at the first time, you can refer the video again, right? Okay. Now in this demonstration, you can actually drag this vernier caliper. So as I mentioned earlier, so this is the main scale. We will go into the details of the parts of a vernier caliper. But before that one, we will understand the sliding movement and how this is been slide over the main scale. So you can see, as I mentioned earlier, this is actually the main scale. The millimeter marked scale is the main scale. And the second one is, this is the vernier scale. So here you can see some special knob-like thing. So this is actually used to drag this one on the main scale. So if you click here and if you drag like this, then you can see here the vernier scale can be moved along the main scale to any position, right? So this is what actually is happening. So you can slide the vernier caliper front and back to any position you want. And you can see here there's a screw. So this screw is actually for the locking. So when you uh, come somewhere here and if you need to fix the reading here, then what you do is you can uh, turn this screw and lock the reading on the vernier scale. So I have actually a real vernier caliper, so I will show you how it is done. But first understand the theory, how it is used here, right? So you can see here actually in the demonstrations in internet, the demonstrations you can see here actually the reading is actually already shown, right? Okay. I hope you understood the principle, the how this one is being moved front and back. That is the sliding mechanism there, right? Okay. Now, then we will understand what are the main parts of a vernier caliper, right? Okay. So I have another demonstration. So here, I think I have in a PPT, right? I think that you cannot see it. Let me share it again. Right. I hope you can see my screen clearly. Right. So here I have given the parts of a vernier caliper. You don't need to draw this one because actually the tutorial also I have given all the parts, but this picture is actually showing the details with much detail. So that's why I use this picture. So in here, sorry, right. You can see here the diagram of the vernier caliper and you can see in the blue color is the vernier scale. So we actually call this the moving measuring jaw. You can call it sliding jaw also. Moving measuring jaw. This blue color one is that one. That is the part that actually that we were able to move back and forth. And you have actually in real life vernier calipers, we have two vernier scales because in some countries they use millimeters as the units. In some countries they are using inches as the unit. Therefore, in real life applications, there are two kinds of scales situated in the same vernier caliper, one in inches and other one in the millimeters. Right. So this blue color one is called the moving or the measuring jaw. And if you go to the other one, the gray color one, that is the fixed measuring jaw. That is the fixed measuring jaw. It is not actually moving anywhere. So it is fixed and this part is moving on that one. And the locking screw is here. So sometimes it is located at the bottom and some designs it is located on the top. So if you see in the right hand side, you can see an actual one where it is taking the measurement. So here you can see the knob is at the top. So it doesn't actually matters. So it is just a screw to tight the measurement, right? Okay. Then you have in the upper side, you have two special shapes like that. You can check the right hand side diagram also. There you can see that one clearly in a real life vernier caliper. So these are we called as internal jaws. We call them internal jaws. So it is given as cross tips, but the best word to be used is internal jaws, because these jaws these are using to measure the internal measurements. Now you can here in the diagram you can clearly see these jaws have been touching the internal hole of the given shape. So the internal separation can be measured by using this one. So in this diagram also, in the right hand bottom diagram also, you can clearly see there. So these internal jaws are being used to measure the internal diameter of a, so this is called a bearing actually. So to measure the bearing of this one, bearing of the internal diameter of the bearing, we are using the internal jaws. As we are taking to measure internal measurements, we call that jaw as the internal jaw. So that is the reason why it is called the internal jaw. And the bottom jaws, the larger jaws are called the external jaws because they are used to take the measurements outside the equipment or outside an object. So you can see here, these jaws are touching the outside of the object. In the this right hand side diagram also, you can clearly see there that we are touching the outside of the object. So this is why the external diameter, here it is measured the external diameter. So we can take the external measurements by using the external jaws of the vernier caliper. So the external jaws actually meaning they are used to take the external measurements. And if you see in the diagram, there's a small we call this one a depth measurement pin, depth measuring pin. So this blue color part is actually internally connected to this pin. So in the real life vernier caliper, I will show you clearly. So there, when you move the sliding jaw along the fixed jaw, this blue color pin also move to the right side. So why we call it the depth measurement pin? Because it is actually used to measure the depths. So in the diagram you can see we are using that blue color pin to measure the depth of this object. That's why it is called the depth measuring pin. Right. Now let me show you the real life vernier caliper that I have. So this one is actually the similar kind of one. So where it is shown in the diagram, you can see in the right hand side. So the similar kind of vernier caliper is with me. Okay, to have a better look on this one, I will stop the sharing right now, and then we'll have a close look on this one. Right. Okay. Right. So can you see this one? Right. So okay, this is the vernier caliper that we mentioned earlier. So you can see uh, like this. So you can, if I make a separation between the jaws, then you can actually clearly observe this one. So here you have the internal jaws. So these are being taken to have internal measurements, right? So these are called the external jaws. And this is that screw that I mentioned, which is being used to uh, lock the reading. So you can lose this one, and then you can easily slide this one like that, right? So if you need to take if you are taking a measurement, then you can keep it like this, and just assume you need to measure the thickness of this one. So what you do is you keep this one here, then you move this one, and you hold it like that, right? Then you tight the screw, then your measurement will not move here and there. Now, if you need, you can remove the object also, then you can read what is the value. right? That is the purpose of this locking screw, right? So now it is not moving actually, though I need to try to move it, it is not moving. So this is the uh, part this is used to move this one. It is like a support to move. Sometimes in some vernier calipers, it is like a roller. So it will roll along this one, right? Now this is that depth measuring pin that I mentioned earlier. So this is how it has been connected actually. So you can see here, this is the sliding jaw. So it has been connected to the sliding jaw from here. So when I move the sliding jaw like this, you can see this depth measuring pin also extending, right, with the sliding jaw because it is directly connected to this one, internally connected, right? Internally connected. So when I move the sliding jaw, simultaneously the depth measuring pin also moving. So you must be very careful when you are taking measurement, right? So you don't do like this, huh? Don't do like this. Don't take measurements like this. It will directly hit your eye. That's why it should be taken like this and take the measurements. Don't ever take it to your face and just drag this one back. So it will hit your eye. So you're getting an injury rather than getting a measurement. So that is not expected by a vernier caliper. So be careful when you are always handling any instrument. Okay, right. I hope this vernier caliper thing is very clear, right? Okay, back to the screen then. Right. So I hope this is clear. Right. Then we will move again to the our lesson. May not right. Okay. Now, as I mentioned earlier, so when the vernier caliper is very correct, for an example, let me go again back to that one. Okay, here. So here you can clearly see if the vernier caliper is very correct, you can see here the zeroth division of the main scale and zeroth of the vernier scale are actually coinciding. What do you mean by coinciding is they are actually uh, in the same line. That is what we know as the coinciding, right? So if the vernier caliper is 100% correct, they should align. If it is not correct, right? If the vernier caliper is not correct, it may be just like this. So even though your jaws are touched each other, okay? So how to check that there's an error or not is to you should uh, push the vernier scale until the jaws are hitting together. So in this one also, this one, you push it until they hit together, and you can see, you can hear a sound also. See, right. It's been fully pushed until the external jaws are touching together. Then you should look at the zero marks of the uh, vernier and zero mark of the main scale. Now, if you check this one, I'm not sure whether you can see this one or not. I am holding as much as closer as possible, right? If you can see this one, here the both the zero marks are exactly coinciding. That means this vernier caliper is 100% correct. There's no any issue with this one, right? There's no any error in the equipment. No systematic errors will be there. So there can be random errors based on the person who is taking the measurement, but it is not possible to have a systematic error with this vernier caliper. Right. So if there are any possibilities to have systematic errors, what are the kinds of systematic errors that we can have? So the systematic error in a vernier caliper we called as the zero error. Right? The zero error is the systematic error which is occurring in a uh, vernier caliper. So you can see here when the jaws external touch each other, zero of the vernier should coincide with the zero of the main scale. If it is not so, the instrument is said to possess a zero error. Zero error may be positive or negative, depending upon whether the zero of the vernier scale lies to the right or to the left of the zero of the main scale. This is shown by the below figure. In this situation, a correction is required to the observed readings. So if you can remember, to eliminate the systematic error, we discussed that we have to introduce a correction factor. We have to add or we have to subtract the correction value, right? So if you go here, you can see in the first diagram, diagram number 1, it is perfectly vernier 0 and main scale 0 are coinciding. Therefore, there is no any 0 in the first instrument. But if you look carefully on the second instrument, here you can clearly see even though jaws are connected, it is not drawn there, but the jaws are touching each other, and you can see the main scale 0 and vernier 0 are not touching each other. So there's a difference, there's a length difference there. So every time now at this moment, you just carefully think, at this moment, actually, vernier caliper should reads a value 0, right? The reading of the vernier caliper must be 0 at this moment. But the problem is, you can see here it is not 0. There is a value. I will tell you how to take the reading, but the value is 0 only if both the zeros are coinciding. If the zeros are not coinciding, that means your vernier caliper is showing some reading. So in the second diagram, it is very clear that the vernier is showing some reading. So it must be 0, but it is not. So it is showing a positive value actually. Because it should be 0, but it is showing a positive value right now. Because the vernier 0 is located right side of the main scale 0. Therefore, we have to reduce the reduce this additional value from the final reading, right? So the correction is a reduction. So to remove the systematic error, we have to reduce. That means the systematic error must be a positive value. That is why I have to reduce. Therefore, we call it a positive zero error. So you can actually remember this one very easily. So if the vernier zero is located right side of the main scale zero, then it must be a positive zero error, right? Similarly, if the main scale 0, if the vernier scale 0 is located left side of the main scale 0, then it is a negative 0 error. So what we have to do is we have to find this 0 error value, and then you have to add that one to the final reading. So if the error is positive, you have to reduce that one. If your error is negative, you have to add that one to the final reading. So that is about the systematic errors or the zero errors. So here you have the description here, shows an example of the positive zero error. From the figure one can see. So there's the blah blah blah. There's the explanation is given there, but you don't need to remember each and every sentence here. Okay, you just take the idea. Try to grasp the idea behind this one, right? What do you mean by a zero error? How do you calculate the zero error? So how do you find the zero error is very easily. First we have to do is you have to bring the jaws together such that they are touching each other. So in your examination, basically in a structured essay, they can ask how do you find the zero error? Then you have to actually explain that. First you have to, the first statement must be your external jaws must be touch each other. Okay, move the vernier caliper such that the external jaws are touching each other. If they are not touching each other, then you cannot actually find the zero error. Therefore, you have to first touch them and check. Okay, that is the important. Now, how to read that zero error value? We will discuss now how to actually read the vernier caliper. So before going to these error calculations and how to remove the error, now that thing we will first see how to read the vernier caliper. How to read the vernier caliper. That is the first thing. Okay. In the tutorial, I have given some examples. So, uh, so have you got the tutorial? Please let me know, because if you haven't yet got the tutorial, then I can share this PDF right now. Okay, I think you haven't get the tutorial yet, right? Okay, right. Then we will do like this. So let me, okay, we'll do like this. So the recording will be there, no? So no issue with that one, because I will upload the recording. So you can actually, when you once you receive the tutorial, then you can actually go with that one. Okay. So so I will share the PDF with you once this is finished through the WhatsApp channel. So the Nexus 12 team will be sharing the PDF with you. Right? Okay. So you just focus on the focus how to read on this one, and you can refer the video on that one. Okay. Right. Okay. Now how to read the vernier caliper. Right. That is what we are going to discuss. Okay. Okay. So it, because it is not actually given there, because uh, when the tutorial comes, then it is easy actually. Right? Okay. Now listen very carefully how to read this one. So I will use that virtual one to show you how to read the vernier caliper. Right? Okay. Now see here. Now the value when all things are in contact, the external jaws are in contact, internal jaws are also in contact, then the value is 0. Now I am moving this one somewhere here. Just imagine I am moving it somewhere here. So just do not just I'll remove this one. Remove this value. It should be removed. Gone. Why? It's not gone. Okay, how it is not going, but however, right. Okay. Now I will magnify the diagram so you can easily understand what how to read this one. Right. Now the first thing is, if I write down how to take the measurement is, so the reading of the vernier caliper, reading is equal to, first thing is we have to find the main scale reading. First you have to get the main scale reading. So how do you get the main scale reading is, so you have to see where is the vernier 0. You can see here the vernier 0 is located here. And you have to check what is the main scale division which has been passed by the vernier 0. So this is the vernier 0 mark. This is the main scale mark which has been passed by the vernier 0. So this is the third centimeter, that means 30 millimeters and 31. The main scale reading is the reading which has been passed by the vernier scale 0. So in here it is actually 31st. Or the 31 is the reading. Main scale reading is, I will put in the brackets here 31, right? 31 millimeters. Okay. Next, what we have to do is, I will write it again. Reading equal main scale reading. We will write down later on that one, plus, right. Now we have to get the least count of the instrument. Least count. We actually have already calculated the least count of this instrument. For this instrument, it was 0.05 millimeters, right? Okay, so for any instrument that we are going to take, we have calculated the least count earlier, right? We know how to calculate the least count earlier. So make sure when you take the measuring instrument with you to your hand, first you have to calculate the least count. Or first you have to find the least count. Without finding the least count, it is impossible for you to read, right? So first thing is find the least count. Then you have to multiply this least count by the number of division, the number of the division of the vernier scale which has been coinciding with the main scale. So then you have to go one by one, checking whether what is the vernier division which is coinciding with the main scale. So if I go from here to here, zeroth mark is not coinciding with anyone. This one is not coinciding with anyone. This one is not coinciding with anyone. This one, no, 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 no. Here, much close, but no. But if you come here, you see here, this is 8 and this is the ninth mark. Just neglect these numbers, okay? You don't need to think about these numbers. Just count the number of divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, without this one, no, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. So ninth vernier division is coinciding exactly with the main scale. Now you have to put that value here. That means vernier division coinciding with coincided with main scale. Right. Now if we read this one, this reading given here, then follow me how to read this one. Okay. So the main scale reading is 31 plus the least count of this one was 0.05. We calculated earlier, multiplied by the ninth one. So if you calculate here, 31 plus 9 into 0.05 means 0.45. 0.45. That is equal to 31.45 millimeters. Right? So this is the reading of the vernier caliper. So it is actually matching with the given value also 31.45. Right? This is how you read the vernier caliper. Right? Hope this is understood clearly. So we will see another example now. Quickly we will go to another example and let's check whether that you got the idea or not. Right? Okay. So I randomly move this one. Okay. I randomly move this one and I stop somewhere. It's better if I can remove it. Let me check whether by refreshing whether I can remove this one. Oh, this I is not actually going away. So, however, we will read this one, right? So I will randomly stop somewhere here. Then I will enlarge this one. Try quickly. Do not look at this answer. You look at the last moment. Try to do it yourself. So you can first get the main scale reading. So it is actually 10. You can see here 10, 11, 12, 13, 14, 15. The main scale is 15 plus, please count 0.05 multiplied by, what is the main scale? Sorry, Vernier division, which is coincided with the main scale. So you check each and every one. Are you here? Find it here. So it is actually 11th one. So that is equal to 15 plus 0.55, and it is equal to 15.55 millimeters. So this is the final reading of the vernier caliper. It is not that difficult. It is very easy to read the vernier caliper. What you need to know is the least count and the new number, the which division is coinciding with the main scale. The number of the vernier scale which is coinciding with the main scale. The other thing is the what is the main scale division which has been passed by the vernier zero, right? So these are the three things that you need to know to read the vernier caliper. Okay, right. I hope this is now clear to you. Then we will try few examples. Okay, right. Here also you have given the vernier caliper, right? If I convert this into normal vernier caliper, right. Now this is a vernier caliper given to you. So quickly, first what you should do is you quickly take the least count. You can easily calculate the least count of this one. Then I will move this one somewhere here. Okay. Try to read this one. I'll try to make it larger a bit. Okay, it is coming a bit larger. Okay. Quickly calculate the least count. Then try to get this reading, value of this reading. So we can get check the answer that you have got it correctly or not. So if someone takes the answer, put a text, okay? So if someone need to calculate the least count, I am putting like that way, so you can easily understand. First calculate the least count of this one. First calculate the least count. Okay. So if you calculate the least count correctly, check whether your answer is correct or not. So first we need to know the what is the length of the main scale. So if you see here, as I mentioned in the previous one also, here this is the vernier zero and this is the vernier first one. This is the main scale value. So you can see here the closest mark to the vernier first mark is actually the fifth one, right? So the total length, if you consider the length of the main scale, that is actually 5 millimeters minus, then we have to find the length of a vernier division. So you can see here there are 10 number of vernier divisions and 49 main scale divisions. So 49 main scale divisions are divided into 10 parts, right? Then you can calculate here the least count. So if you take the common base, you can write it as 50 minus 49 In the numerator, 59, 50 minus 49 divided by 10. That is basically 0.1 millimeters. Right? So this is the least count of the instrument. Right? Okay. If you have got this one correctly, very good. Then we will read the diagram. So I will move it like that way, somewhere here. Okay. Now how to read this one is, first you need to identify where is the location of the vernier zero. So this is the vernier zero. So what is the mark? What is the main scale reading? So this is the fifth one, sixth one, seventh one. So 7 plus least count 0.1 multiplied by the division of the vernier scale which is being coincided with the main scale. So if you check one by one here, you can see the fourth one is the division. Right? There's no any other division coincided, right? The fourth one is the division. So we have to put 4 here. So then you can write down the reading 7 plus 0.4, that is actually 7.4 millimeters, right? Okay. So this is how do we read this one. If someone get that one correctly, it is good, right? Okay, because but as we can see, it is the fourth one. It is coincided. So I think I got an answer 7.4 millimeters. Good, very good. Right? Right. Okay. Now we will go into the examples in the tutorial. Okay. So quickly go with me. So in the first, so for all the vernier reed calipers given here, the least count is actually 0.1 because this is the normal laboratory using vernier caliper. In the laboratory using vernier caliper, this is the usual vernier caliper that you can see. Here you can see only 10 divisions. So usually this one mean 10 divisions mean 9 main scale divisions are divided into 10. So this is the basic vernier caliper that we have. The previous one, this one. This is the school vernier caliper that we have, right? Okay. Therefore, always take the least count as 0.1 millimeters. For each and every vernier caliper example given here, up to 8, and for others also it can be up to 8, the least count is 0.1 millimeters. Now what we have to do is we have to write the reading of each and every one. Okay, right. Let's take some time and let's try to do this one quickly. So I will keep the screen like that. So there are 4 vernier readings. Okay, quickly do this one. Okay, now if you go to the first example, now please closely look at this one with me. So what we need is first is the main scale reading. So how do you get the main scale reading? Main scale reading is given by taken by checking the vernier zero. So we have to check what is where's the position of the vernier zero. So vernier zero is located here. So what is the main scale mark, the main scale reading which has been passed by the vernier zero? So this is that one, right? This one is the mark on the main scale. So what is that millimeter mark? Which millimeter mark is that? If this is the 9th centimeter, usually this is measured in centimeters, marked in centimeters, no? So this is the 9th centimeter, that means 90th millimeter. If you count back 90, 89, 88, 87, 86. So this is what? 86. So the main scale reading is 86. 86 plus. So the least count is I have said 0.01 multiplied by. Then we have to find the Vernier division which is coinciding with the main scale. So this is the zeroth Vernier division. It is not coinciding with anyone. First one not coinciding. Second one is perfectly coinciding with any mark of the main scale. We do not require the mark. What is the value of this one? We do not require this one. We only have to count the Vernier divisions. Which Vernier division is coinciding? So this is the zeroth one. First, second. Second one is coinciding. Therefore, you have to put 2. So your reading is should be 86 plus 0.02. That is 86.02 millimeters. Sorry. Here the least count is 0.1, no? Therefore 86.2 millimeters. Not 02, 86.2 millimeters. This is the answer for the first one, right? Similarly, you can do the second one also. So if you go to the second one, you can see here clearly the main scale reading is actually 0, right? The vernier 0 has passed only the 0 mark. Therefore, the main scale reading is 0 plus least count 0.1 multiplied by the number of vernier division coinciding with the main scale. You can check one by one. Oh, here. This is the one which is coinciding with the main scale. So that is the sixth division. Therefore, that is 0.6 millimeters. Right. Second one, 0.6 millimeters. That's correct. Okay, good. Most of you have got 0.6 millimeters for that one. Very good. Third one, very easy. This is 70, 65, 64, 64 plus 0.1 multiplied by the vernier division is 1, 2, 3. Third one, therefore it is 64.3 millimeters. If you go to the fourth one, easily you can take it is this is 10th one, therefore 10 plus 0.1 multiplied by sixth division is coinciding, therefore that is 10.6 millimeters. Okay. Okay. We have got the answers correctly for. Okay, very good. So please others also try. I'm getting answers. Others don't just wait. Just don't think that you will be covering this one to the recording. Okay, that is never going to happen. I know that one because looking the recording and doing this one, it is not actually successful, right? If you miss something, then it is better if you can watch the recording and check. But when you are in the class, please try to engage with the activities. Right. Okay. Now we'll move to the next one. Quickly, this do this for also. Quickly get this done. 5, 6, 7, and 8 also. Quickly do. 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 5, 6, 7, and 8 also. If someone can give the answers before I write the answers, better. Okay, good. I'm getting the answers. Very good. Yes. Right, good. Next one. Final one is 71.5. So, sorry, the seventh one. Eighth one, final one. It will be 2.4. 2.4 millimeters. Right. Good. Sorry, in the previous one, this is not 71 actually, no? So correction from my side. There's a correction from my side. It should be 70.5, right? Okay, I will clear this one. This is not 71, this is 70.5, right? 70.5 millimeters. Okay, correct. That's a mistake by me. Not 71. It should be 70.5 millimeters. Okay, right. Good. So most of you have done them correctly. Very good. And then we will move to the next part. So there are two other examples also. Okay, we will do quickly. We'll do these two examples also quickly. Write down the readings quickly. Don't take much time. Please be careful. Please be adhere to what I have said and get the answers. Ninth and 10th. Okay, we'll check the answers now. So the time is enough actually for you to answer. So we'll check here. So where's the zeroth mark? Don't get misled by the edge of this one, right? Most of the time when someone is giving the vernier caliper like this has been done in the A levels also. They think this line is as the zeroth one. So this is not the zeroth mark. Please be careful. Your zero is located somewhere here. So you have to count up to here. So 21, 22, 23, 24, 25. If the main scale reading is 25 plus 0.1 multiplied by, what is the division coinciding here? That is 5, 6, 7 division. Therefore, this is 25.7 millimeters. Do not put 70, right? This is completely wrong. Huh? Do not put 70. It is 25.7. That is the accuracy level, not 25.70. For this vernier caliper, we cannot take up to that much. So if you come to here also bit tricky. So if you go here 31, 32, 32 is the main scale reading, then 0.1 multiplied by, now we will look closely. What is the coinciding one? So 1, 2, 3. The third one is coinciding properly. All the others are not actually coinciding well. Right? Only the third one is coinciding properly. Sometimes you may feel the second one is coinciding, but actually it is not actually getting directly on the other one. Third one is the one which is very much coincided. So it is 32 point here 0.1 multiplied by third one, that will be 32.3 millimeters. So don't worry, in your A-level examinations, they will enlarge this part again and give you. For the tutorial, I didn't give you, but usually if this is giving in an A-level examination, they will definitely make this part again enlarge and give you, so you can easily read the marks. Okay, right, then there are no worries on that one. So, but here this third one is the one which is coinciding there. Right. So because I am taking the image from some book, then to take when the image resolutions may be changed, and you can see there's not that much sharp edges are possible to take when you are taking a screenshot or something, right? So that is why you can see only there are two divisions coinciding, but actually the real one is the third one is the one which is coinciding properly, right? Very good. You have done the examples correctly. So well done on that one. Okay. Now we'll move to the next one, that is calculating zero error and uh, correction values. How to get the corrected values. Right. So zero error is not a strange thing now. It is just a reading. Zero error is actually a reading. Now if you go to this example where we discussed about the zero errors here. So actually zero error is the reading right now. Reading right now. Now you can easily read this one now. So the least count is 0.1. Therefore, you can read this one. Main scale is 0. So if you read the reading of this one right now, 0 plus 0.1, 0.1, 0.1 multiplied by the fifth one. They have the least count, sorry, so the zero array is 0.5 millimeters and it is located to the right side of the main scale 0. Therefore, it should be a plus 0.5 plus 0.5 millimeter is the zeroth error. Now, when you find the negative zero errors, you can see here clearly this has been moved to the negative side. Then you have to find the negative zero error. So the best way to find the negative zero error is to read the scale backwards. What does that mean? So when you are reading from left to right, here if you are reading from left to right, you take this one as the zeroth mark and this one as the 10th mark. So when you have a negative zero error, it is best to read from the back side. That means you better take this one as 0 and this one as 10th one. So you are reading the reverse way. Instead of 10, you are taking it as 0. 1 you are taking as 10. That means you are counting backwards. Right? Okay. Then your main is your ninth value is the 0, 1. Here there's a ninth mark, ninth millimeter mark. No, ninth millimeter mark is your 0 now. So the here the zero error will be 0 plus 0.1 multiplied by coinciding value. Now we have to count from the back side. This is the zeroth one. 1, 2, 3, 4, 5. Fifth one. So here also the zero error is 0.5 millimeters, but this is a negative value. It's a negative value. Negative 0.5 millimeters because it has been, you can see here clearly, it is left side of the main scale. So if it's a positive zero error, you can read like we did earlier. But if it's a negative zero error, please read backwards. That is the most safest method to find the zero error. There's a way to find the zero error from the front side also, but it is bit risky and sometimes there may be confusions. But there is no confusion if you read from the back side. Just put a minus sign in front of the value. So you can easily identify whether it's a positive zero error or negative zero error just by comparing the positions of the main scale zero and vernier scale zero, right? Okay. I hope this is fine with you. So then we will do some examples of calculating the zero errors. Then you will understand more on this one. Okay. Now we will go to the exercise. Okay. Here I have given, assuming that the jaws of the vernier calipers are tightly closed, find the zero error of the vernier calipers below. Right. Now we have to find the zero errors here. Now in the first one here also I will do the first one myself. If you can do it yourself, please try to do it yourself. Okay, I'm supporting here. Now you just look at the zero positions. You can clearly see the vernier zero is located left of the main scale zero. Then definitely there must be a negative zero error. This is not a positive one. This is a negative zero error, right? So if it is a negative one, then you have to read from the back side. So the 9th millimeter is taken as the zero and 1, 2, 3 like that way. That's how you read. So the main scale reading for the backward reading is 0 plus. So it is a negative zero error. You better put a negative mark first. Negative 0 plus. So 0.1 is the least count multiplied by. Now you count from here. Sixth one, right? So sixth division is coinciding from here. If you count from the back side, the coinciding mark is the sixth one. So therefore, if you close the bracket and then you simplify, that is minus 0.6 millimeters. So the zero error is minus 0.6 millimeters. Right? Hope this is clear. Then you come here, quickly write down the vernier reading. So the main scale is 0 plus 0.1 multiplied by number of divisions coinciding is 6. Therefore, this is positive 0.6 millimeters. Right. Right. Now let's do other two also. I did two for you as an examples. Now try to do other. So you have 3, 4, 5, and 6. Okay. Quickly do this one. Find the zero error values of each of them. Right. Okay. Now we will go one by one how to calculate the zero errors. Right. So we will go to the first one then. So once you directly see this one, now you know this is a negative one. Right. This is a negative zero error. Once you see, you can clearly see the zeros are not matching and it is located. The vernier zero is located left of the main zero. Therefore, it should be negative one. So better put the negative mark there. And now here, now you read from the back side because it's a negative zero error. So the ninth mark is considered your zero value. 0 plus 0.1 multiplied by, what's the division? 1, 2, 3, and fourth division. Therefore, negative 0.4 millimeters is the zero error here because this is the zeroth 1, 2, 3, 4. Fourth one is the coinciding one. Now, if you come to here, this is a positive zero error because the vernier zero is located right hand side of the main scale zero. Therefore, 0 plus 0.1 multiplied by the number of divisions coinciding is third one. From the front side, now we are reading that is 0.3 millimeters. Okay. Now, if you go to the fifth one, this is also negative one. Therefore, you can start with the negative mark. Put a negative mark and start. Negative 0 plus here the least count is 0.1 here also multiplied by what is the division coinciding 1, 2, 3. Third one is the coinciding one. Therefore, minus 0.3 millimeters is the zero error. So if you come to here, you can clearly see it is 1 millimeter shifted. Therefore, this is a positive zero error. It is 1 millimeter directly. You don't need to actually find. You can easily take this as 1 millimeter because this zero in so zero of the vernier scale is directly coinciding with the first millimeter mark. Therefore, the error is actually 1 millimeter. Okay. So if you have get these answers, then very good. If you have tried this one, that is also very good. Okay. We'll move to the next one. Okay. You have two other examples. Not two, 10. There are 10 examples actually. So quickly do this one and get the zero error value. Sorry. Okay. These two Vernier calipers. Quickly get the zero values, zero error values. If you go to here, you can clearly see that the first mark is already passed and second mark is not passed. So this should be 1.1. 1 point, sorry, 1 plus 0.1 multiplied by the number of division is ninth one. Therefore, this is a positive zero error and it is 1.9 millimeters. 1.9 millimeters. Right. If you go to the next one, it is a minus one. Sorry, it's a negative zero error. The negative mark, you better first put the negative mark, then you check here. So this is the ninth mark, and this is the eighth mark. So this is taken as zero, and now it has the vernier zero has passed already the second mark in the main scale. This is the zeroth one. This is the first one. First mark is also completely passed. That means your error should be starting with 1 plus 0.1 multiplied by the number of division is actually the second division is coinciding 0, 1, 2, 2. Second division is coinciding. Therefore, this is minus 1.2 millimeters. Right. If you have got these answers correctly, good. Then you can check 9th and 10th one also quickly. If you do this one also, what are the values that we are getting? So once you directly see, you know it is a negative one. So negative, put negative mark. Read from the back side, that is 0 plus 0.1 multiplied by the number of division coinciding is sixth one. This is minus 0.6 millimeters. If you go to here, it is basically a positive zero error. That will be 0 plus 0.1 multiplied by 1, 2, 3, third one, that is 0.3 millimeters. 0.3 millimeters, right? So these are the zero error values of the vernier calipers I have shown, right? I hope all of you have get this correctly, right? Now we have to do the correction of each of them. So now you know the correction actually. So if you have a positive zero error, what you have to do is you take the final reading and subtract the positive zero error from the final reading. If you have a negative zero error, then you have to add that value to the reading. You just do not consider about the mark. Just check whether it is positive or negative zero error. If it is a positive zero error, just remove that value from the uh, final value. If it is a negative zero error, just add that value. I am always saying the value. Do not consider the sign, add the value, right? Okay. Now, this is the first real example that you have the zero error even in the first figure, and in the bottom figure you have the reading taken. So what we have to do is we have to write down the final reading. That means the corrected reading in the dotted lines. Now for the first two, I will tell you how to do this one, right? Then you can continue for the others, right? Now, as mentioned earlier, in the first diagram, we have to find the zero error. So we will find the zero error quickly. So I will write down near the diagram. So you can see here it's a negative zero error because it is located, the vernier zero is located left of the main zero. 0 plus 0.1 multiplied by, so you have to read from the back. So this is the ninth one. Therefore, this is taken as the zeroth one. Therefore, this is the zeroth of the in the vernier side. So one, two, three. Third one is coinciding from the back side. So your zero error is negative 0.3 millimeters. Now what you should actually do is you have to add 0.3 to the final reading. So now you have to find the reading of this one first. So the reading of this one is 0 plus 0.1 multiplied by the number of division coinciding is actually the sixth one. 6. This is the reading of the instrument, but you have a zero error. It's a negative zero error. Therefore, you have to add the answer, add the value, add the 0.3 to this one. So it will be 0.9 millimeters. So this is the actual reading of the instrument, 0.9 millimeters. This is the actual reading, corrected one. Now, if you come to here also, now first you can calculate the zero error of related to this one. So once you can calculate that one easily, 0 plus 0.1 multiplied by the number of division is here 1, 2, 3. Third one is the division. Therefore, 0.3 millimeters is the zero error, but it is a positive zero error. Then we have to reduce this value from the final reading. Now, if you go to this one, so you can read the first take the reading of this one. So 10 millimeters already passed. Therefore, 10 plus 0.1 multiplied by the division which is coinciding is the sixth one, right? Then to take the corrected reading, you better subtract that error value from here, right? So you get 10 plus 0.6 minus 0.3, that will be 10.3 millimeters. So these are the final corrected readings. I hope this is clear to you. Right. We'll do the other example. So you have two examples here. Question number 3 and 4. Okay, quickly do this one. Right. Okay. I hope you have done this one also. So here also, when you look at this one, it is very clear that there is a negative zero error. So first we calculate the negative value. Negative zero error, negative. You better count from the backside. 0 plus 0.1 multiplied by the number of division is 1, 2, 3, 4, 5, 6. 6 division. Therefore, the zero error is minus 0.6. Now, if you read the reading here, you know that it is this is 70th one, this is 65th, this is 64. Therefore, 64 plus 0.1 multiplied by the coinciding division is actually the third one, 3. And this is minus 0 error. Therefore, you have to add that one plus 0.6. So it is 64.3 plus 64.3 millimeters plus 0.6. That will be 64.9 millimeters. Okay, now if you come to here, the final one, then you also can calculate the zero error of this one. But here also be careful when you see a negative zero error, please read from the back side. Here also you can clearly see this is the ninth mark and eighth mark is also being passed. Sorry, therefore it should be putting as 1 millimeter minus, first put the minus sign, minus 1.1 plus 0.1 multiplied by the coinciding division is actually second one, that is equal to minus 1.2 millimeters. So if you take the reading from here, that is 32 plus 0.1 multiplied by number of division coinciding is third one, but you have a negative huge value plus 1.2 line. So 32.3 is the final reading, 32.3 plus 1.2. 32.3, then 33.5. 33.5 is the final answer. Right. So these are the answers of this one. Hope everyone agrees with me. Hope all of you have got these answers properly. Right? Okay, very good. So you have got the answers correctly, and that is very good. So this is actually about the Vernier caliper. There's nothing much strange on that one. This is a very simple topic and very simple instrument. Right. Okay. Now you have an idea about the main parts of a vernier caliper and how to use that one and how to read the vernier caliper. Right. So the tutorial also there are some few examples you can do that one. So in the bottom of this lesson, so there's another part. Actually, it should be discussed before the traveling microscope, but somehow when I am attaching the papers, I think I have missed that one. So that is the extended vernier scales. So extended vernier scale is the vernier scales with actually a higher number of main scale divisions, right? So extended vernier scale is designed to obtain very small measurements and easily readable vernier scale with gaps of calibration not so close to each other. So when you read the diagrams here also you get confused that sometimes you see that two uh, s- marks are coinciding with each other at the same time. That is because the separation between these two divisions is very small. So to remove this one, they have constructed vernier calipers that I have shown earlier, like that one. So you can see here the separation between vernier calipers is significantly large. Then it is easy to read. So they have constructed the vernier calipers like that, right? So this kind of vernier calipers are called the extended vernier calipers. So the vernier caliper that I have already shown to you is also a type of extended vernier caliper, right? So here also that is how that the vernier caliper we calculate the least count is given here, right? Okay. Then there are other special kind of vernier calipers known as the circular vernier scales. So there's nothing much strange about this one. This is simply the vernier caliper that you see. Only the difference is rather than measuring for millimeters, this is measured in degrees, angles. Okay, for the circular scale is used to measure actually the angles rotated. So in the experiment, what we call as spectrometer, you have to use the spectrometer instrument. So in the spectrometer instrument, there's a circular vernier scale. Then you must be able to read that one. So there's no much difficulty here. The only thing is, you seems this is much difficult because we have different numbers written different ways. But keep in mind the angle. Usually the angle can be measured in both sides, right? You can measure an angle either in clockwise direction or in the anti-clockwise direction. That is why you have two directions. You have values marked to the two directions. Here you can see 0 in the middle and you have 10, 20, 30 in the right hand direction and 10, 20, 30 in the left hand direction. Because actually this is marked to the both sides is because the angle can be measured in either sides. You can measure the angles either clockwise or either anti-clockwise. For that purpose only they have given in the both the two directions. And the bottom one is the main scale. The top part is the vernier scale. So please take a note on that one. So this upper part is the lower, sorry, is the vernier scale, and the lower part is the main scale. Right here, what has they done is here we have taken actually 29 divisions. 29 divisions are divided into 30 parts. So a single vernier division, single main scale division is actually 0.5 degrees because you can see here 1, 2, 3, 4, 5 like that way degrees are going there, but you have marked in half degree notations. So after 100 and so if you go like this way, it is already reducing 140, 130, 120. Then this should be, so you are going by 2 by 1 by 1. Therefore, this is actually 19.9, sorry, 119.5 millimeters, 19 18.5, 18, like that way. That is how the reading is read. So because we have marked in the half degrees angles. So third 29 number of half degrees is divided into 30. So that is the thing that they have done. So the when you're finding the least count, what you have to do is you have to reduce not from 1 millimeter, not from 2 millimeter, but from half millimeter. Sorry, so from here degrees, no, half degrees minus 29 divided by 29 divided by 30. So if you take the common denominator here, you can clearly see here 30 and 2 is there, half millimeter is there, right? No, we have divide side like that way, no? Yes, then you can take the common base, then you have 2 and 30 is there, 29 divisions, right? 29 of half divisions, sorry, 29 half degree divisions, 29 half degree divisions. So this has to be again divided by 2, which is giving you 29 over 60. Right, then you can take the common base, right? Then you can take the common base. You have to multiply 30. Then 30 minus 29 means 1 over 60. So the least count is actually 1 over 60 degrees. Usually this is denoted as 1 minute. Minute. In angles, there's a special thing called minute, right? So 1 degree is equal to 60 minutes. We call like that. Each 1 degree is equal to 60 minutes. If I write it separately, the relationship 1 degree equals 60 minutes. 1 degree equals 60 minutes. So this is the relationship between degrees and minutes. So you can read actually this part. This is also not much difficult. This is very simple. You can easily if you understand the Vernier principle properly, then you can easily understand the circular Vernier scale also, right? Okay. This is basically the end of Vernier Caliper, and you have few examples from here also from the Vernier calipers. There are different types of questions that has been already asked, right? So before going to any other equipment, so first we will see why actually we need to learn this Vernier caliper this much. What are the types of questions that we are getting from the Vernier caliper in our examinations, right? So I have actually specially selected 2020, 2014 paper as I can remember. Just let me check. So I didn't was not able to get the 2014 English medium one. I think it was not available there. So I have taken the singular medium one but don't worry about the language. Just see what are the things that they have asked, right? So what they have actually given it's a small cylindrical object and you have to find the density of this one. So if you need to find the density of some any object, what you have to do is first you have to calculate the mass of that one, then you have to divide that one by the volume of the equipment. So mass you can calculate by using an electronic balance and you have given a Vernier caliper to find the dimensions, and then you can calculate the volume of this one. Right? For that one, you need to take the measurement. So the vernier caliper is the equipment that you have already given. Right. Right. Then what they have asked is, so if I go one by one quickly, so they have asked about the initial steps that you should follow before taking a measurement. So what is the first thing that you do? First thing is you have to check the zero error, or you have to first find the least count. Okay, even before finding the least count, you have to actually, in order to understand how to calculate the least count, first thing is you have to actually keep the uh, what we call it external jaws in contact, and then you can count the number of divisions. So that means when you touch the external jaws, you can understand the about the zero error. So the first thing that you should need to do when you take a vernier caliper to your hand is actually check whether there's a zero error or not, right? Then actually you can calculate the least count. So both of these must be determined at the first stage as the first step, right? Therefore, they have asked what is the first steps that you follow. So see, they are actually questioning the practical scenarios. They actually questioning the practical scenarios. So then you have to write down an expression to how to write the density. And then they have asked what are the readings that you are taking from a vernier caliper. So there you have to write down. First thing is the zero error that you have to first measure the zero error. Then you have to measure the heights and diameters. To measure height and diameter of the given cylinder. Right. Then they have given the readings of each vernier each time that they have used the vernier caliper. So you have given actually 5 times. The first one, second one, third reading, fourth reading, and fifth reading. You have given 5 readings, and you have to write them down in this table. So this is actually the marking scheme that I have taken. But here you have the places, the spaces given, dotted lines are given. Then you have to write down the readings value. So if you do not know how to read the vernier caliper properly, you won't be able to answer this question, right? Therefore, please understand this is very, very important. Reading the vernier caliper is a very important thing because in 2020, 2014, they have really checked whether you can read from a vernier caliper or not, and whether you know how to calculate zero error and other things related to vernier caliper. Right, if you see here that the marks have been given, it is mentioned how the marks have been given. So it is very important when you are doing an examination question from a structured essay or from a essay question, please make sure that you follow the marking scheme to mark the questions, because they are the people who are deciding to what point that they are going to give the marks, right? So if for an example, if it is here, if the total table is correct, then you can get 4 marks, right? If not, if if you are if 3 answers of third column is correct, at least 3 answers correct, then 1 mark. You see, if your whole table is correct, then you get 4 marks. If not, your marks will be reduced. Then you have to write down an expression like that way, and you have to simplify and get the answer. So there are other questions also, right? From the vernier caliper, even from the MCQ one, they are just asking questions from the vernier caliper. So you can actually go through that one. So 2020, 2014 paper, it is an important one. Please do that structured essay question, right? So I will share the PDF also of the structured paper so then you can go through that one easily. Okay, right. Then we have to talk about the screw principle and the micrometer screw gauge before moving into the traveling microscope. Right, before moving to the traveling microscope, we will discuss about the screw principle. Right, screw principle and micrometer screw gauge. So there are readings actually that we cannot take from Vernier caliper also because Vernier caliper has an accuracy of 0.1 millimeters normal laboratory one. Therefore, the maximum, sorry, therefore the minimum reading that you can take to have a error less than 1% is 10 millimeters. So if you are measuring measuring lengths less than 10 millimeters, then your percentage error will be very high through the Vernier caliper. Then you need a more accurate one. So more accurate than the Vernier caliper. So the micrometer screw gauge is the most common apparatus that is used instead of Vernier caliper to measure smaller lengths, right? So first we'll understand what is the screw principle and micrometer screw gauge. Right. First thing is the screw principle. Now you know if you need to tight something, tight some screw or lose some screw, you know exactly what to what direction that you should actually turn it. Right. Even without conscious, you are actually, if I ask you to remove the internal internal tube of the uh, your pen, then what you do is you quickly unscrew from the bottom and take it out. But when I say you to unscrew, then you really know to what direction that it should rotate to get it unscrewed. And also you know that if you need to fix it again, then you know what is the exact direction that you have to rotate, right? Because there's a standard that is being followed to construct each and every screw in the world. So that is the screw principle, or we call it simply the right hand rule. The right hand rule. So the right hand rule is something like this. You can keep your fingers bent like that, and then you can keep your thumb pointed in the perpendicular direction. It's like something like a like button, no? Like button in Facebook also, like button, like that way. So if your fingers are represent the direction of rotation, then your thumb will direct the direction where it will move linearly, right? Because if you consider some screw type thing, when you unscrew, what happens? For an example, I will take this vernier caliper. So you can, I think you can see clearly. So I will take this one. This is a screw, no? So if I turn this one to this side, you can clearly see that the separation between this knob and the vernier scale is gradually increasing, like that way. So when I turn it like that way, it actually went to this side. So I am doing is the turning motion, but screw is converting it into a linear motion. So screws are the best method to convert circular motion to or rotational motion to a linear motion. So you rotate the head, but pin is coming out linearly. So you rotate the rod, pin is going in linearly. So actually the screw principle is a principle where rotational motion is converted to the linear motion. So the detail is given here. And some important things to be known about we need to know about the screws. So I have actually saved an image to do that one. Let me check. So it is actually not included here. I think the screw principle. So we look at an animation how this is working, right? And it has more complex machineries are shown here, right? However, because think I have not included here, right? Okay. However, I think I understand the concept by looking at this example, right? So when you rotate this one, what happens is this one is moving linearly in and out. That's what actually is happening, right? So the same principle is used by the micrometer screw gauge. So you can see in the diagram that this is the instrument that we labeled as the micrometer screw gauge, right? So today I will take just an introduction onto the introduction onto the equipment. Then we will discuss in the last next week. We will discuss how to read the micrometer screw gauge, right? So here we have the. Let's understand the parts of this one. So this is called the frame, and this is called the anvil, and this is called the spindle. And you have a locking finger here, and a sleeve with the main scale, and a rotating scale, thimble, and a ratchet head. So these are the basic components. Okay. Now let me show you how this is actually working. So I have a few animation ready. This one, right? Okay. Now see here. Now you can see the parts also here. This is the frame section. This is the frame section. This is the spindle. Sorry, this is the anvil. This is the spindle part. And this is the main scale or the sleeve. And this is the circular scale because it is divided. The circumference of this one is divided into equal parts. And this is called the thimble, and this is called the ratchet, right? So if you need to take a measurement, what we should do is you have to keep your measuring object in between the anvil and the spindle. So how you need to have this one separated, no? So for that one, you can rotate this one from the thimble. So you can see I have rotated into the downward direction. So if you apply the screw principle here, so you have to turn it towards my side. You have to turn it towards my side, right? Toward turning like this way. So you can see here clearly the screw gauge is moving to the left hand side. If you need to turn to the other side, you can see here it is turning to the other side. Right. So you here keep the object and then you tie it from here. Right. So if I show a place where the measurement is taken, then it is something like this. Sorry. Like this, you can see here. So this is a ring like structure. So you have keep that structure in between anvil and the spindle. So from the ratchet or from the thimble, you can rotate this one. So when you are rotating, what happens is this spindle is moving towards this one and the spindle is hitting this one. Then it tries to tight the object in between anvil and the spindle. Then what happens is, if this is something like a rubber, then what happens is the shape of the object will get deformed. If you put a rubber ball here or rubber wire here or rubber tube here, then what happens is when you are applying the pressure, then this one will get deformed. Then you cannot measure the actual value. So to avoid any over tightening, there's a special mechanism called ratcheting mechanism. So the ratcheting mechanism thing that they do is, when you keep an object and then you turn this one to move the spindle towards that one. So once this is tight to a sufficient level, then what happens is this ratchet structure work to give you a tick tick sound. So what happens is, when this one is uh, tight in between anvil and spindle to an adequate level, then what happens is this and thimble will try to slip. So that means it give a tick 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 sound, but it will not move the spindle. Furthermore, it can be rotated, but it will never move the spindle again back towards the object. Right? So you can see here clearly the main scale, which is marked in upper side is marked in millimeters and bottom side is marked in half millimeters. Okay, this is top part is millimeters, bottom part is half millimeters. So they have a very much accuracy. So usually the main scale of the micrometer screw gauge is usually up to 3, 4, or 5 millimeters, but the circular scale is basically divided into 50 or 100 terms, right? So one specialty about this micrometer screw gauge is actually the least count or the pitch. So actually pitch means the linear distance traveled by the screw when it is completely rotated one cycle. So you take a nut, and what you do is you completely rotate it by one cycle. Then you can check how much distance that it has moved front, right? So the pitch is something like that. The distance advanced by the screw when it makes its one complete rotation is the separation between two consecutive threads. This distance is called the pinch of the screw. Sorry, pitch of the screw. So without knowing the pitch, actually we cannot calculate the least count. So you can see here in the diagram, in the paragraph also, I have given the how to calculate the least count of a micrometer screw gauge. You have to find the pitch, then number of divisions in the circular scale. That is how the least count is calculated. All right. Okay. So today actually we will finish from here because there's a issue from my side also. So as we are not taking the interval and we are not taking an interval, so I can actually my target was actually to complete the vernier caliper today, but also I was able to actually complete a part of the screw principle also, right? So then Thursday we will completely focus on how to read the micrometer screw gauge. So similar in the vernier caliper, I have prepared a lot of examples for you to try. So I think most probably sometimes your tutorial also may be reached within next couple of days. It may be reached to you. So then we can do actually, right? From both sides we can do. So here also don't worry. As you understood the vernier caliper, I am going to give you the full knowledge on the micrometer screw gauge, how it is read, what is the zero error, how to calculate the zero errors, and what are the things to be considered when we are things that need to be considered when we are using a micrometer screw gauge. I will try to bring a real micrometer screw gauge But I'm not sure actually whether I will be able to get it by Thursday or not. But we'll check. We'll see. If there's any possibility to show you, I will show you the real life micrometer screw gauge. So in the diagram, it may be seemed very larger one, but actually this is very small and you can keep it in your palm, right? You can keep it in your palm. It is very short because the maximum distance that can be measured from here is around 3 to 5 centimeters, so very small distance, right? Therefore, it is not uh, that much big. It's a very small one, right? So we will discuss on that one. So if you have any queries on the Vernier Caliper side, please let me know now so we can have a quick discussion on that one. Right? It seems there are no any questions. So actually today we can finish at this time. And next week, sorry, next day onwards, we will continue, and we will complete the micrometer screw gauge by next Thursday. And as per the plan, I think we will be able to actually continue as per the plan. So if you have any questions, please don't hesitate to ask. I'm always encouraging you to ask questions. So if you are unable to ask within the class, please you can add to the Nexus 12 group, or you can personally text me uh, through my my WhatsApp number. So if I am available or if I am free, then I will definitely send you an answer. If it is not possible, then I will discuss in the class also the question that you have asked. Okay. Then if there are no any questions from your sides, then we can close for today. So thank you very much for joining. So if you have any questions, please put to the text and wait until your answer is given to you. Okay. Then no questions. Thank you very much for joining. Okay. Have a nice day. Good night.